Okay, I think we'll go ahead and get started. I'd like to welcome you all to our seminar and also welcome our simulcast universities at Manitoba, Calgary, Alberta, and UBC. I wanted to make a quick announcement before we get going today that next week's talk is the only one that's not in this room. It was due to a scheduling issue that had been booked quite some time previously. So we will be in the Arts Building, room 241 next week. This is for Irina Creed from Western University. There will be some email announcements about that, but I just wanted to remind everyone that the venue will change. So, and I want to thank again Howard Weider and the Global Institute for Water Security for funding of this series. And it's a real delight to welcome Efi Foufoula-Georgiou from the University of Minnesota. Efi is in the Department of Civil Engineering, but she wears many hats at the University of Minnesota. She's the Distinguished McKnight University Professor. She's the Joseph T. and Rose S. Ling Chair in Environmental Engineering. And she's also the Director of the National Center for Earth's Surface Dynamics. And she served in this position, for over 5 years now. Efi came to the University of Minnesota after a PhD at Florida, with a small stint in between 24 years ago. And in that time, she's really defined herself as a thought leader in ecosystems engineering and some of the topics you'll hear about today. Her work has been recognized in many ways. She's probably one of the most awarded scientists working today that I'm aware of, with the Hydrology Sciences Award from AGU, a Fellow of the American Meteorological Society. She is the Dalton Medalist from the European Geophysical Union and a Fellow of the AGU. I think what's actually speaks of Efi as a person is that in addition to these accolades and her work in research and her work directing this Science Technology Center, which is I think $40 million center or enterprise at the University of Minnesota, is that she has really embraced a number of community efforts through her involvement through various societies. So she's president-elect of the AGU Hydrology section. This is a big job. Leading up to that, she is on the Horton Medal Committee of AGU. She chairs, as I know, the AGU Fellows Committee, where we've worked over the last year. She's on the executive committee of Kawashi, and has been the chair of the Horton Medal Committee at AGU. These are huge tasks, and I think really speaks to Efi's engagement and commitment to the field. So it's a real delight to have Efi here with us, and she's going to talk to us today about river networks, dynamic connectivity, and resilience. Efi.
Thank you very much. It is a real pleasure to be here, and thank you for inviting me. And the real pleasure is for two reasons. The one is I had excellent discussions today, and I look forward to more tonight. And the second reason, which makes me very happy, is to know that there is a place colder than Minnesota. I don't think in the 24 years I have traveled to any place in the winter that was colder than where I started. So today I chose to talk about this problem, but I will start with a little background on myself and the place I come from. So the current research of my group, I can classify it in 3 areas. The one is precipitation estimation from space. The second is sediment turbulence and river topography coevolution. And the third is landscape dynamics and the response to change, being that climatic or anthropogenic. So in the first area, estimation from space, I have been involved with NASA's TRMM, the Tropical Rainfall Measuring Missions, for more than 15 years, and I am in the science team for the Global Precipitation Mission. And the problems currently we're working on in my group is how to incorporate estimation about non-Gaussian structure of precipitation, and especially extremes, if it is in time, sharp weather fronts, or in space, rain cells that are embedded within lower intensity precipitation areas into estimation problems. And estimation problems are several, including downscaling, fusion of precipitation data from different sensors, each with its own resolution and its own accuracy, and data simulation, which is use the observations optimally with the model for initial condition estimation and prediction. And the second problem, which is more recent, is how to deal with structural model uncertainty, not an uncertainty or a model error that is additive and usually Gaussian, but it is in the structure of the model. For example, an easy example to give you is, suppose you have a process that moves along with an advection diffusion equation, and you have problem in the diffusivity parameter, meaning it is a structural time-varying diffusivity parameter, but you assumed it constant. You're going to get different predictions, and they will not match the observation. How do you incorporate that in a data simulation scheme? And I have here some publications. You can see these are all recent ones. The second problem, which goes really from the large scale down to very small, centimeter scale to meter, the questions of interest is, what is the multiscale structure of bed topography? If you look in a river, you will see that it's far from the textbook organization of bed forms, dunes, anti-dunes, and so forth, but there are topographic features at many scales superimposed on other features at different scales. And of course, this interact with the turbulence, this define the turbulence, and both together, they give rise to the sediment transport flux that we care to characterize and estimate in any river. Results there range from really providing very recently a more elaborate classification of turbulence above a moving bed form, and characterizing the what's so-called magnitude intermittency coupling. Another thing is, of course, the characterization of the non-tailored behavior of moving bed forms. Every scale moves at its own pace, and characterizing this multi-scale velocity is, again, important for building improved sediment transport models. And work that I've not talked about is, of course, all these things move, but give rise to the stratigraphy that we see in any core, and how can we go from the evolution to stratigraphy and stratigraphy back to the evolving landscape. So landscape dynamics and response to change. Some years ago, and this is the only paper that I have here, in 2010, it's not very recent, it's 3 years ago, we promoted the idea that all the transport laws, especially say in the hill slopes and other landscape evolution models, they basically are local in the sense that they will tell you in a hill slope that the sediment flux is proportional to the local slope, and that would give rise to diffusive flux, or it's non-linearly proportional to the local slope, say slope square. This is, again, a characterization which is local. But of course, we know that there is a lot of what I would call collective behavior, that if I sit at the point of the hill slope and I measure the flux, that flux might not come really from that point, but in a small period of time, sediment fluxes generated above collapse together and arrived at the same point in a very small interval of time. And this gives rise to the so-called non-local transport laws that are characterized through fractional integral equations. What is the signature of climate and geology on river network structure that was approached in one of the recent work? And what I would like to talk about is, how do we define resilience on river networks? This is new ideas, they're not published, so you will be, I will be looking forward to your reaction. Now, this work, and where I'm a member in civil engineering, but I have another office, and my group works at the so-called St. Anthony Falls Laboratory. This is the downtown Minneapolis, and the lab is here. Was built 75 years ago, just across the St. Anthony Falls, which is the largest falls on the Mississippi River. And we take advantage of that because there is a bypass here that passes the water of the Mississippi through the lab, and we run the experiments. And this is the first floor of the lab, but it goes 5 floors down with lots of experimental facilities that run year around. There was an abandoned spillway here that was not used by the Army Corps of Engineers for the past 30 years, and we took advantage of that, and we've created the so-called outdoor stream lab, where we tried to kind of bridge the scale between the very small scale laboratory experiments and the real world. And you can see here we have semi-controlled, basically, and very high experimental equipment for studying processes from sediment to meandering rivers to biological activity in streams. These are some of the facilities of the lab, a delta, basically evolution. This is the landscape evolution under climatic change. This is a large flume, 70 meters long and 3 meters wide, and so forth. And the field data. Now, Jeff mentioned the National Center for Earth Surface Dynamics, that's a science and technology center, which we just finished the 10 years, but they liked that so much, so they renewed us for another 5 years in what we call NCET 2. So imagine 12 years ago now, almost, we proposed a center that had the goal to predict the dynamics of the couple processes, water, sediment, biota, and how they respond to climate, land use, and management change. And we were really an interdisciplinary team with all these institutions headquartered at the University of Minnesota and having cooperative agreements with 11 other institutions. And of course, these other institutions offer also facilities, not only our lab, but it was the Berkeley rotating drum here where we studied debris flow, the Venture lab at the University of Illinois, and the University of Texas Austin lab. And we selected 3 sites. I'll talk about one today, but one was close to Berkeley in California. The Angelo Coast Range Reserve is a very pristine site with very high sediment, again, and landslides and so forth. The other is an agricultural basin in the Minnesota River Basin. And the other is a delta. Because after Hurricane Katrina, of course, the message came home that these deltas are starving because of withheld of water and sediment from upstream. We chose the Wocks Lake Delta, which is a beautiful delta that you see here, which was formed naturally over the past 30 years by a diversion of the Mississippi River through the Atchafalaya River and grew by itself, not only in geomorphologically, but biologically. And this is a laboratory by which to study delta processes. So the context of today's talk is the following. Climate change, human actions change landscapes across many space and time scales and in many interacting processes. It's a chain of events. For long-term planning, very highly specialized, high-resolution models that are over-parameterized, for which you need to calibrate and possibly over many years, horizon. It's difficult to even know what changes and how the model parameters will change. We need simple conceptual frameworks that can reveal at least trends, synchronizations, amplifications of extremes, threshold behavior, and where to concentrate more, at what locations, at what times, and possibly what processes amplify and therefore magnify change. So the basin that we are studying, not only in my group, but as a part of an NSF Water Sustainability and Climate new big project grant, is the Minnesota River Basin. As you can see here, is in the upper Midwest. You see the Minnesota River Basin here, and this is a smaller sub-basin that I'll talk about. So it is 44,000 square kilometers basin. It drains in the Mississippi River, and it is so much, the water is impaired under all EPA standards. And the problem is excessive sedimentation. So there was a referendum in 2008, even by the state, by which several $1 billion are set aside to clean up the waters because they affect biological life, and of course, they affect downstream a very iconic lake, which was formed as a remnant from the glaciation period. And I show you here from 1500 up to now, the sediment, which has been extensively studied through the course in this Lake Pepin. So you see in the 1500, the sedimentation rate was of the order of 80,000 tons per year, and now it is tenfold, 800,000 tons per year. And not only that, but you see that the blue is what comes from the Minnesota River Basin, which is only 37% of the total waters that drain into the lake, but contributes 80 to 90% of the sediment. So where is the sediment coming from? How does it propagate and how does it store? Now, there was a major perturbation, and you're very familiar here in that region, 13,000 years ago in the glaciation period. So a lake here and several others catastrophically drained. Lake Agassiz drained here, creating a base level 4 of 70 meters, to which, so this is the main stem of the Minnesota River Basin, which is like 600 kilometers. And you see the tributaries hanging over that, trying to still adjust to the base level fall. If we go to the smaller basin that we have extensive instrumentation, this Lasher Basin, what again you see is that before 13,000 years ago, of course, the river was joining here. The catastrophic 70-meter base fall is still propagating and has propagated 40 kilometers upstream, creating a terrain that above the neck zone, it's very flat and agricultural. Within the neck zone, there's steep bluffs and eroding surfaces, both under rainfall and, as I'll talk about, accelerated hydrologic cycle. And of course, the 95% of the land is agricultural land. And again, you're familiar here. And this has created, since the 1950s to 1970s, a completely different picture with the incredible miles and miles of drainage tiles that are put into the agricultural land to drain more efficiently and increase the productivity. The effect of these drainage tiles, and not only, because I'll show you there is precipitation extreme, also amplification, is that since 1930 to now, and this is normalized by the 30 to 70 period, any measure of stream flow, mean annual flow, peak daily flow, the minima, etc., have been amplified by a factor of 5. A lot much water is coming down the rivers. And I have data, and many colleagues have worked on even documenting over the past 20 years the widening of the rivers. Now, at the same time, precipitation, and this is an analysis from daily precipitation, say the period 48 to 77, and after 1977, you see the exceedance probability curve, the IDF curve, telling us clearly that the extremes have been amplified. We do have, and there are many people that have documented that, shorter duration, more extreme magnitude events. Now imagine now then, more extreme short duration events accelerated by a factor of 5 stream flows, going through rivers that in many places, the river is very much adjacent to a bluff, which is 25 meters tall, vertical. You don't need very much to undercut it and then have it collapse and contribute to the sediment. And floodplains with other, not so nearby, 40-meter away, paleobluffs. And then the rivers that are still adjusting themselves and cutting back, creating ravines that also contribute to the sediment. So one thing that was documented as part of NSED over the past few years is the following very interesting picture. That yes, we do continue to have a very high sediment production still, which has not accelerated, but it is pretty much stable over the past decade. But with many techniques, including isotopes and radionuclides and beryllium and lead, etc., there has been documented a serious regime shift in the sediment sources. I will not go into the details, but this, the beryllium, etc., tells you that the larger the magnitude of that, the more the surface topsoil that is contributed to the sediment, and the smaller the magnitude, it comes from other sources. So you see that although the sediment rate remains the same, in the last few years, the sediment load is high, but the sources of that have shifted from topsoil, agricultural lands, to near bank sources. And this, if this was here, would be topsoil. That this is there is the agricultural land is not contributing really to the sediment, but this accelerated hydrologic cycle from the indirect effect of tillage drainage has taken the banks, collapsed the banks and reaches the bluffs, delivering to the streams different type of sediment. Coarser sediment works the rivers much faster than they used to before. And of course, that has an effect on the biological life, the aquatic communities. As you can see here, species richness is declining. And not only, this is the productivity, here is for the south central Minnesota, is below what should be for human-dominated landscapes, because the water are kind of very sediment-laden. With that, I'd like to get into a framework by which possibly we can think about long-term planning and understanding sources, sinks, and response. So if I look at the schematic of a river network, and every link is characterized by several properties, and I was talking to some of you this morning. It could be, of course, the length. It could be the incremental area that drains to that link. It could be the drainage area upstream of that link. It could be the slope of that link, the flow, the width of the river, the depth of the river, velocity, the time delay of substance within that. It could be, which we are starting incorporating, the proximity of that link to a bluff, how wide the floodplain is around that link to contribute or not contribute sediments and so forth. So every link has a lot of properties associated with that. It's almost a tag, an identifier for that link. Now, if we look at the distance to the outlet, two links, for example, 2 and 3, could be the same distance from the outlet. And if we look at so-called the width function, which is the function of the links at the distance from the outlet, this will be the very well-known width function. It just tells us how many links are at what distance to the outlet. But at the same time, when we consider transport of water, of sediment, of gravel, of sand, of a pollutant, this thing is rearranged because the velocities start being quite different. And from the distance to the outlet, if we get to transport time to the outlet, 2 and 3 might be separated for quite a big time, a different time. So it's kind of stretching the network and therefore stretching also the width function to a time response function, which could be completely different and dependent both on the topology and the geometry and the process dynamics. So if we look at the Minnesota River Basin here and you see the distance from the outlet, this is the basin outlet, it's colored here. The width function looks like that. It has been computed. That's fine. But the question is, how can I use that in all the very peculiar, you see the network is not, it's a very geologically kind of impacted network that we have here. How can I come up with a hydrograph, sedimentograph, politograph, or whatever else we want? I'll give you the example of sand, because sand is 30% of the sediment in that basin. Sand transport velocity. I will just, for interest of time, go fairly quickly, but we compute the characteristic velocity of sand from a volumetric transport rate, assuming that, say, a percentage of the total depth, say 10%, participates in sand transport. We have the depth and the width of the river at that point, and of course we use hydraulic geometry to change that as we go downstream. We assume a normal flow and a transport formula that someone can plug a different one. We use the Engel and Hansen formula that use the shear stress of the bed and so forth. Now, if you put this together, and if you also use, and we've used 110 stations to really quantify the hydraulic geometry, we can parameterize the characteristic velocity or virtual velocity of sand in terms of a few parameters here. You see the velocity of the water, you see the height, and you see the slope. And if you go one more step to include the hydraulic geometry, you see that the velocity, virtual velocity of sand, is really dependent on the upstream contributing area and the slope is amplified to the power 1.5. The steeper it is, the faster the sand would move. And someone can come up with a different formulation here, but this is kind of beyond the point to illustrate what we're talking about. So we see now that distance is one thing, but slope is another. And if I plot these slopes here, you see that this is a plateau, actually, it's called a coteau that is left back again from glaciation period. You see a lot of steep, still undercutting streams close to the main step. This is the high slopes. Okay, so this slope now projects itself into sand velocity non-linearly. So the velocities again here are definitely non-uniform and definitely not really proportional linearly to the distance from the outlet. So the sand transport time, another element that we have to, of course, velocity, to take me from a velocity and distance to a time, we have to do that properly. We have in small basins just do the whole computation with real hydrographs, but for the whole 44,000 square kilometer basin, the assumption that I'll present here is that the sand moves or does not move. It moves when we have bankful flow, does not move if we have flow below that. And this introduces what is it called the intermittency factor, that is basically sand moves 17% of the year under bankful and does not move the rest of the year. Everything calculated such that the volumetric mean annual sediment load is preserved. The bottom line is that we translated now distance and other geometric properties like a slope, upstream area, hydraulic geometry, and so forth into a time, which then takes us from the width function to a process-based scaling, and that's for stream flow. But for the sand is this stretching of the basin. And of course, you can partition every basin here that we want. We can see what its response function would be. And here, just for reference, you see that stream flow would take around 200 hours, this is normalized, to flow to the outlet. Sand takes a very long time. And depending, this is like 0.1 millimeter sand, but if it was a different grain size, that time would change. So what good is that? If in the 100 years down the line, which is, it's not very far. 100 years we see now, close to Minneapolis with Corin and so forth, the arrival of strata of sand that were released years ago in the headwater streams, far up in the basin. So let me propose like the following even simple application, that if we have then quantified a response function that has this form, which is dictated by the river network and all its properties, then you easily see that if it was a new event, being that a storm or a human impact that affected the headwater streams and therefore released a new pulse of sand through the basin, then you can see that a 40-year period between the two events would really synchronize and amplify a peak that was coming from this basin to a peak that is coming from this basin, coinciding. So this is the response to the first, but it's coming from this upstream basin. The second response would come from this basin and would amplify an outlet to create a unexpected, a superposition of the extremes that have come from two diverse parts of the basins. The distance is not really an explanatory variable. But this is only the response. If I wanted to partition the basin and see how all the fluxes, in that case sand or whatever else, was really propagating through the system, we can go one step further, and instead of just looking at the response, do what we call parcel tracking, network transport model, where we not only question the outlet, but we see the organization of these parcels or whatever substance it is throughout the network. So we can specify this, the parcel inputs, grain size, the volume, etc., where they're released. We can assign delay, and the delay we assign here is based on the sand transport kind of example. Track the location of each parcel, allow for storage if they exceed a transport capacity and so forth. One can easily do all of these things dictated by the system properties, and we can expand later, which we've not done it so far, that is allow new inputs even to be generated internally. As the system propagates and probably erodes the banks, new input is created. So if the initial input, for example, was a pulse at every headwater stream, okay, these are the headwater streams. It's all too full, but this is the first order links of the whole basin. And you know, the one parcel could be 1,000 parcels, it doesn't matter, but just a disturbance in the headwater streams only at t equals 0, and allow these inputs to transport to the outlet. Probably I can play if I can. Here, you can follow, this is very fast. If you look at it carefully, you will see, as I begin, I was like, where do these flux appear? Because it is stored for a long time in a very flat link, and then all of a sudden starts aggregated downstream, and you see its presence over time. So let us define a cluster as the set of adjacent links with at least one parcel. Could be 10 parcels, etc. It doesn't matter. This is a threshold set by the process of interest. So this is a cluster of 5 consecutive links that are occupied by that substance. What we expect, of course, in that system is that as the time passes, the number of clusters will decrease over time as parcels aggregate. So they are all parcels starting at the headquarters, the first order link. They start propagating downstream. They form bigger clusters. We start here at time t equals 0 with, this is 1,000 parcels, which is as many, or it's 10,000, 1,000 parcels, as many as first order links we had in the basin. Then some of them coalesce, and as we go down, the number of clusters decreases. Of course, the clusters become larger. We see, interestingly enough, that there is a time, so T1, these are the clusters. And you know, you have to enlarge to see. They are just all over, of course. They're connected paths that have this substance, in our case, sand. It could be anything else. At time T2, you see, if you projected this line there, you will see that it would be a different you know, trajectory as what it is. So at time t equal 2, we see a regime shift in some sort of as time doubles, the number of clusters reduces by a factor of 4. It's a very rapid reorganization of the system. That this time arises from the system. It would be different for every system. And what you see is that the clusters start coalescing in a much faster rate. And this is because they started reaching the main stem, and you know, they keep their connectivity. And then they reach the main stem, and then this release that is here is basically reaching the outlet. That's one cluster just came out at the outlet. If we look at, so this is the number of clusters. And of course, as the number of clusters goes down, the size of the clusters goes up. So if we look here at the largest cluster size, as the time, again, evolves, interestingly enough, within the time, this T2 to T3 of rapid reorganization, we see that the maximum cluster size was formed, not only absolute maximum, but a running average, so a very robust average maximum cluster size, within that rapid reorganization period, where the clusters basically at every instant, they change, but the maximum cluster size remains largest throughout this time period of Bayesian propagation of the flux. I'll come back to that later if the time allows, but for those that are familiar with you know, variability of system and connectivity in terms of a possibly reorganization to imply or at least be a precursor of a system change, you see that within that time is not only the maximum cluster size, as I said before, but it also, I don't show here, the variability of that cluster size. It is this period, T2 to T3, is what I would call the faster breathing state of the system. That is, the clusters coalesce and then break up at the fastest possible rate, making both the size of the cluster and the variability over time of the size of the cluster to give me the coefficient of variation maximum during that period and close to the maximum cluster size. This is something that I'll come back later because it denotes the characteristic time scale of the system, that if you wanted to keep that connectivity at that level, you better interfere at that point and not at that point. Gives you a characteristic scale. So the premise and the hypothesis here is that dynamical connectivity of the system in terms of substrate on the bed or a biological activity, mussel population, or some other substance changes, of course, as input vary in space and time, and they're transported downstream. But the ecosystem functioning in a basin has organized around that connectivity. It would be a different ecosystem if this connectivity of sand bed, for example, was all over the place in small chunks, or if I have a part of the system that maintains its connectivity for some period of time. So the premise is that ecosystem functioning has organized and contributes to organizing this regime that maintains the dynamical connectivity of river fluxes. And the question then is posed, if we cared to understand system resilience in terms of how well the system is connected and how long it stays connected. And the typical definitions of resilience are several, but I would like to at least discuss two. Resilience is a measure of the ability of the system to maintain function. If function relates to connectivity, then it's a good measure of resilience in the presence of disturbance or change. A similar and related definition is the buffer capacity, the system's ability to reduce the direct influence of external perturbations and avoid shifting to a new regime. So for understanding system resilience, that a lot has been done in mathematical ecology, but not on river networks or on network systems, but on spatially explicit systems. You have a box, everything talks to each other, and depending on, say, if the climate becomes more dry or less dry, et cetera, you develop different patterns of connectivity of vegetation and so forth, but not on propagated through networks. We have to understand the system characteristics that could contribute to resilience as a measure of the ability of the system to maintain function when the disturbance changes, and understand when the system moves from one regime to another, and therefore understand how fluctuations, say, in breathing time are natural or they are really precursor to a change. So if I go back then to the system that we were talking about on the river network and ask the question, how robust is the system for maintaining a level of functioning through dynamic and collectivity as inputs are reduced? So my disturbance is not have all the headwater basins contribute to the network. And I want to propose a plot here within which we can study this system, that here I'll have disturbance. In our case, percentage of inputs. This will be fully supplied system. All headwater streams are supplied with flow or sand. 50% of the system is supplied, 25%, 0% is applied. And here is the level of system functionality, which is the dynamical connectivity that we explained before, under different system perturbations. That is, when I have 100% of the system supplied, I'll have the maximum functionality of that, maximum cluster size. And the question is, where does the system plot itself in that space? I would argue that null resilience is when I have 50% withheld of the system supplied, that is only 50% of the system is supplied with that substance, or deprived of that substance, and this responds linearly. That is, 50% of the system gets connected. That is, a maximum cluster size falls to 50% of the maximum possible cluster size. That would be that you change the system and it responds in a linear way. And this is functionality loss because you could have the system functioning at 100%, but it's not. If you supply it less, it functions at a less capacity. At the same time, I would call a system low resilience when, of course, you disturb it in a way that you deprive 50% of that from an input, and the cluster size or connectivity goes down dramatically. And that is the functionality loss, again, because the system does not reach its potential in that example through a connectivity that supports ecosystem functioning. High resilience would be a system that sits up there, again, for the same reasons, that 50% deprivation of the system in terms of an input does not reduce the connectivity much. And the functionality loss is small. At the same time, for the systems we're talking about, another thing of interest would be, suppose you want to prescribe the level of functionality you want the system to operate on. And suppose it is here that is, not very far from the maximum capacity and functionality of the system. And then you can ask the question, what do I have to do to the system? How much do I have to supply to that system such that it performs at that level? I see that akin to, some of you might have been familiar with the so-called and famous planetary boundaries, in which you define basically the safe operating space. We can talk about defining the safe operating space for ecological functioning on river networks based on connectivity and thresholds that would make this environment conducive to the ecosystem that we care about. And of course here, someone can define anything. I talked about connected cluster, even if it is, one parcel per link, but we can impose any threshold and look at the system in what I would call a raw cluster, meaning exceeding some capacity, which would break the system and define the connectivity in a different way, but the same conceptual framework would exist. So going back to the example, what would happen if we had the system that we supplied 100% headwater links are supplied with sand? And again, for this basin, the sand is important. For this basin, the headwater streams are steeper, and they do supply under more extreme precipitation sand to the whole system. So what about if we stabilized, or if we changed the landscape in the hill slopes of the first order streams, and only 50% of them supplied sand, or 20% supplied sand? Where would that system fall in that space? So we look at this, again, the level of system functioning based on the maximum cluster, which we chose as a metric of the dynamic connectivity, versus percent of system activated. And through lengthy calculations, it takes a little while to do this on a large basin, and at every point here you see 5 points, because there's 5 different realizations. When I say 50% of the first order links, which 50%? Selected at random. But it is enough to say that it's pretty robust to that, which speaks for this curve really, which the system puts itself, is a pretty robust position of that system relatively to the process of interest, which again, in this case, is maximum connectivity in the substrate of the bed that is covered by sand. And that means that if, for example, we change the operations, human or otherwise, in that landscape, and only half of that was supplied into the system, then the maximum connectivity would just change by 70%, or would be reduced by 30%. That's a robust, it's not a super robust, but what will be interesting, and we will continue to do that, is depending on the process, depending on the system, we will expect this curve to move up and down. Interesting question would be, what would make this system less resilient? But I will not go into that, but just give you the idea that less resilient such a system will become only when an external perturbation will disconnect part of the system. Suppose you go and break up through a process which is external to this disturbance here. You eliminate a link and you cut off the connectivity. That's the only way you can have the system go into less resilient space. I will go quickly through that. So all these things that I talk about so far, I started with time evolution. I took you to spatial distribution of connectivity. And I want to make sure that you know that every point here, say the 100% disturbance, the 50% disturbance, I could put an axis here, which is time, and see how the system evolves in that time. This only gives me the maximum cluster size, but this cluster has evolved over time. It has a period over which it preserved itself, and it has a period at which this cluster size disconnected completely and fell out of the basin. So going back to the 100% supplied system, the plot that I had before, where we have the faster system breathing, I want to say that for that specific system, you see that as the fluxes start propagating, there is not really the main stem, but pretty close to the main stem, a time scale over which you maintain the maximum connectivity, and it is dynamic connectivity because it is over time and persists. And then, of course, as you start getting into the main stem, you are getting the input out of the basin. But if you really wanted to, this is an example again, and I want you to think broadly as to what connectivity would mean for what process. But if someone asks the question, I would like to maintain the system in the maximum connectivity possibly, as I said before, there is a characteristic scale of the system that this plot allows me to see, which is if I supplied, for example, so this would be something that you don't want to reach, a state at which the cluster starts shrinking down. If I wanted to supply the system such that I preserve this cluster, of course, if you, as I said before, if you get it here, you just unnecessarily supply the system too early, and you don't help it maintain the maximal connectivity for as prolonged a time as you wish, because you supply it too early, and then you have to repeat this application for maintenance of the system. So it gives you a characteristic scale where a second input, I call it, or a second disturbance have to be applied such that you maintain connectivity. As I said before, in spatial ecology, lots of work has been done, and some of you probably have read, where basically they look at the system, a dynamical system, and look at its potential, and you might have a bistable state and so forth. And one of the characteristics of the system getting out of bounds and getting from one stable state to another stable state is nothing but the correlation coefficient or coefficient of variation, for obvious reasons, because if the system is in a potential well which is too narrow and very stable, it moves around it, but there's not much place to go. So the standard deviation and the correlation is very small. If you have a flat well that the system can, back and forth until it jumps to the next state, this is very unstable situation, and the coefficient of variation and so forth goes up. This is the coefficient of variation, akin to what I was showing before for this maximum reorganization state within the river network. There are lots of ideas that have to be studied. But going back to the whole picture, I started with the premise that we do have systems that are too large. They respond to change at time scales that are too large, again, to study in a very much detail. But there are decisions to be made. Should I develop this place of a watershed or the other place? Or if a change happened here, could it synchronize with another change that happened here, and they all came together at the same time? Do I know what disturbance in the system would just be the best or the worst for a specific species and so forth? This is a study probably some of you have seen. It came out, Watershed 2100, I call it, EPA. Minnesota River Basin is indeed one of the basins examined here, and I want to just basically have the main finding of the study, which is what we all know and we experience very much in our systems there. Higher peak stream flows increase erosion and sediment transport. Lots of nitrogen and phosphorus are increasing in this watershed. Many watersheds are likely to experience significant changes in the timing of a stream flow in the pollutant delivery. There will be a tendency to shift from snowmelt-dominated spring runoff events to rain-dominated systems, and we are seeing this. And this changes in the 10, 20-year behavior. And changes in the nutrient and sediment loads are correlated with changes in the hydrology, as again we've seen in these basins and many around the world. So I would call this a cascade of changes and perturbations that you have to study in a systematic way, because all these cascades happen on a system that is basically expressed in the landscape, is the river network, okay? But every one of these changes, the hydrology, to the sediment, to the biology, have different time scales. And it's very important to see them as a connected whole, operating all of them in a, many times, very large basin that is interconnected through a directed tree. So as an epilogue, I conclude by saying that we need simple conceptual frameworks to study how climate and human-induced changes propagate in connected landscape system. River networks I talked about, extended river networks we talked with a lot, the hill slope paths. We need simple frameworks to define system-wide safe eco-hydrologic spaces within which to operate in a response to change, and dynamical connectivity which associates with system functioning could provide a framework within which to study resilience and response to perturbation. Thank you.
Thanks very much, Efi. Time for questions. Howard?
I really enjoyed the talk, Efi, and I think you gave us a lot to think about. I have a question of clarification and then a substantive question. So in terms of the connectivity maps that you were looking at and the parcels and the linkage and so on, I didn't understand what the driving hydrology was for that and what assumptions that you were making.
Bank full discharge.
Aha, okay.
So in smaller basins, there is no difficulty in just basically doing the hydrology right in small basins, and we've done that in a pretty small basin, not 44,000 square kilometers for 100 years down the line. So as I said in the slide, that they had the assumption of sand transport. The assumption, which is kind of typical one made, is that sand would be transported mostly under bankfall flow and very little under lower flows.
And what is the duration of bankfall flow?
The duration of bankfall flow it's a 2-year flow. So we use all the flow duration curves. We found the bankfall flow for each one of the 114 stations so forth. And then we computed the mean sediment load for every basin and projected, as I said, through this intermittency factor, the percent of the year that the system under backfall flow would transport the same sediment. And that was like 17% of the year. How many days is that? Would have the system transporting sand and the rest no.
Okay, thanks for the clarification. So the question is, of course, you have a population of sediments of different sizes, and you presented one grain size, but of course there are lots of issues around the fine sediment fractions, which are much more mobile. So I wonder, I mean, presumably you would expect quite a significant distribution as a function of grain size and material type and cohesiveness. So the network connectivity that you're looking at is actually just one particular snapshot of a much more complex
Absolutely.
pattern. Yeah, okay.
Absolutely. In fact, even the formulation that I have, and let me not go back to the slides, it has the grain size just there as a denominator. So if you change it by a factor of 2, you get different timescales. And if you integrate, which is it's not very difficult, probably could be implemented through the particle tracking. If you use a whole sediment size distribution, you're going to get a different picture.
And wonder whether you've looked at the uncertainty around the transport equations, because there's huge amount of variability in the process understanding just for a thing called grain size. So how robust are those networks to uncertainty or underlying assumptions about transport?
So if you accept the assumptions here, which is, again, transport, normal flow, bankfold initiation, and the formula, the Gilland formula, etc., then for me, one primary assumption that has to be investigated and we've not done is integration over the grain size. There is no one single size. And looking into that to assess how the response function changes. If, for example, they took pigs, mobilize and become different, that's a very big thing. But if you tell me to go back and do all the uncertainty analysis in terms of the fact that mobilization is done in a threshold type of behavior that is not only the shear stress of the bed, but it depends on the precipitation and the flash flood that comes there, etc. I agree with you, it has to be done. It's conceptual framework that I'm developing, but the conceptual framework could flip around very quickly if the envelope of response functions becomes so large that connectivity, for example, let me say that we're doing now some of the uncertainty analysis, and we've not seen that curve, for example, move around too much.
Okay. Thanks very much.
Sure.
Other questions? Students from the Journal Club who didn't get a chance to ask a question.
They've been asking me questions, so.
Yeah. While you're thinking of that question, how does the terrestrial portion come into this? We talked about this a bit today, but for a labile nutrient like nitrate, in a picture like that, the nitrate coming into the stream could be many decades old, and it relates to kind of the transit time of that water through the subsurface en route to the network. Once it's in the network, it's a very quick time scale relative to that multi-decadal transit time, for instance, in the terrestrial side. I'm wondering if you've thought of that or how one begins to bring that into these kind of network connectivity concepts.
Yeah. In principle, as we've talked before, it is possible because, again, you have other paths, and then it's not only the river network, it's the other flow paths that are not fluvial, they're not imprinted there, but they exist and they bring these other fluxes. Their time scale of delivery is comparable to the time scales I'm looking at here, long time scales, and they could change the picture. So, as we talked before, I mean, we've not addressed this issue, but at least for robustness and sensitivity analysis to see if the framework is even viable, I would imagine starting with a characterization of these other flow paths that reach the river network, a process of them delivering to the to the real streams the nutrients or nitrogen and so forth, and see what the difference it might make downstream if we work within a operating uncertainty in the delivery of that subsurface to the mainstream. So I want to emphasize here that there's a lot of uncertainty, and is even more uncertain, in my opinion, if we started with very distributed, parameterized models that cannot take us in the long time frame that sometimes we want to have for decision in such a large basin. So, under the premise that connectivity does the job, it is up to us then to do our best. And the fluvial system is not very difficult because the river network is there. So what we have to worry about is, transport, process-based transport, delivery, storage, which I didn't talk about. Storage is another thing that we've not incorporated, because in 100 years, as sediment is transported, it changes the bed and changes the storage capacity, but this is something that could be handled. So it is up to us to define the paths over which we think flow of fluxes happen. And then within a framework of connectivity, we believe in that. I happen to believe in the connectivity which is intermittent in space and time, and therefore activated or deactivated, not only because of external perturbations, but internal, inherent dynamics of the system.
Yeah, I
But
mean
in
that
principle, they can be incorporated in the framework.
that diagram from the GenSco paper was a nice illustration.
Oh, yeah, of course,
that
yeah.
might vary down the-
very down. This has been inspirational in the sense of, yes, it's an on-off process.
Yeah. Okay, looking at students, leaders of the paper discussion today. Yes, James.
So, with the, when you're talking about a particular particle being eroded or whatever at the headwater and then moving downstream, does it show up as a lost link if that particular particle is of a size that it can redeposit on the river somewhere in its transit and not make it all the way through the river system to the outlet in the same event? And then what happens if that happens? What would happen if it is then eroded again later on from not a headwater anymore, now it's somewhere midstream? How do those things fit into this conceptual framework?
So, right now, all the particles that are released show up in the time that, in that case, was the 100 years or whatever it is, they show up in the outlet. But most likely, what happens in any real system is you have, very long storage times, and these particles re-emerge from other parts of the system. Okay, if they're lost and buried forever, you have mass loss. But in a very large time scale, you don't have this much mass loss. It appears, but in time scales that are beyond what we're interested. So again, conceptually, it's not difficult to incorporate storage and release because it shows up as a different time scale of a link relatively to that particle. And this is what we started doing, that is introduced. By the way, I did show you here, for this sand simple transport law that we had here, if you ask me, so what is the distribution of the time, transport times through the links? It's very interesting that altogether, both the slopes, both the links, and the width of the channels and depths end up having a very thick tail probability distribution of the travel times of the links. That is, there are some links that delay the transport by a lot. So what I want to say is that it all depends on the process of how these things move through the system to map themselves into a delay time in that link. So I don't know if I missed something, but the particles as we have them here, they start at the external links and they go through the system. They can be delayed, but they never deposit and die. They could.
Good.
And I mentioned it at the beginning that every link also has, not as we implemented it, but the potential to have new mass or new flux generated in that link because of its vicinity to a bluff. And that would be an additional thing, not difficult conceptually to incorporate. That is, you can say that if the flow reaches bankfall or above bankfall, and it is that specific link adjacent to a bluff, you have a new input of that many particles or whatever flux in that link at that time.
Okay, it's 5:05, so I think we'll draw it to a close. Efi will be at Alexander's after, holding court, discussing more about networks. Hopefully you can join us. Quick reminder about next week, different room. It's over in the Arts Building. Watch for the flyer that Leslie sends around. And thanks, Efi, for a really stimulating talk.
Thank you.